Good morning, students. Welcome to Experimental Stress Analysis, Module 3, Class 1. See, today's topic is photoelasticity, and in the previous two modules, Module 1 and Module 2, we have learnt how to determine the stresses like principal stresses and principal strains, and you have learned how to determine the deflections in a member by using certain strain measuring elements like strain gauges, strain rosettes, and you have come across how to determine the stresses and strains by using certain strain measuring elements like strain gauges and strain rosettes. Today we will be discussing about a new topic, that is photoelasticity, how to determine the stresses in the member by using the new technique, and that is called as photoelasticity technique. Here the photoelasticity is also an experimental technique which is used to determine the stresses and the strain in a particular member, in the sense any member which is in complicated shape as well as which is subjected for a complicated loading conditions. This approach or this technique is more appropriate rather than the analytical techniques which we used for calculating the stresses and deformations in the members. So the name photoelasticity reflects only with the nature of experimental methods. Here the word photoelasticity indicates, the first bit indicates photo implies the use of light source and the optical techniques, while elasticity indicates the study of stresses and deformation in an elastic body. See, this photoelasticity technique is widely used in many problems where the members are subjected for what you call as complicated loading conditions. And one best thing about this technique is where the stresses and strains can be calculated very easily within the member at any point. It also provides a quantitative, many components, very quickly we can measure the stresses and strains as well as deformation developed in the member with high accurate values. And one best thing about this technique is the stresses even at the interior points, also along even at the anterior points, also at the surface levels we can determine what is the behavior of the member, that is what is the deformation of the member on the surface and within the body. Along with that one, we can determine very easily the stresses and strains developed in the member by using this technique. And this one and photoelasticity technique, where we can be used for any underlayer or the sublayer, what you call as deformations of the members. See, one major thing in this topic is photoelasticity is we can determine the behavior of the member, that is such kind of you can take a prototype of any model, and that prototype is made up of certain transparent materials. So these transparent materials, when they are subjected to load, they are tending for deformations, and when we are using a light source for this variation of the deformations, we can determine very easily the stresses developed in the member. So the transparent materials, either it may be plastic materials or it can be a silicon wafers. So now let us consider certain applications of the photoelasticity techniques. The first one, you can observe a silicon wafer is nothing but a circular, what you call as a disc made up of silicon. It is a very thin layer, and whenever it is subjected for an external load, there is a deformation of the member. To determine the deformation of a member, when we are using certain light source, and this light source when is passed over the surface of this member, you can observe clearly there is a variation in the total colors of the total entire disc. See, because of the application of load, there is a variation, different variations of the colors takes place. These variations of the colors will directly indicate where the stresses are concentrating more, So here it is very easily used, which can be used for analysis of what is the stress developed in the discs rotating members. So those such kind of rotating members can be taken as a prototype, can be created for such kind of members, and he can analyze those prototypes. Similarly, the application of photoelasticity can be done for a structural members like a trusses as well as the beams. Suppose if it is trusses, if it is subjected for an external loading, so we need to determine where the stresses is taking place, the maximum deformation, as well as the where the stresses are distributed in this what you call as truss element. So we can determine very easily how the truss is behaving based upon the external loading conditions. So here also we are going for a materials that is called as a transparent materials or a silicon material or a rubber materials. So it is very easy, or which is applicable for your truss problems. Along with this one, the photoelasticity application can be applied for analysis of the safety spectacles in industries, and we can prevent the failure, or we can justify where the material is taking place whenever the spectacles are opened and closed. So the joints, can observe here the joints which are subjected for maximum stress. So the area at this point can be varied because of the data which is obtained from your photoelasticity technique. So here by this one we can prevent the failure of such kind of member. Along with this one, a structural member like beams can be analyzed very easily. So here one such example is a cantilever beam which is subjected for point load. Because of the application of load, there is a deflection in the member from fixed end to the free end. So the maximum deflection from the fixed end to the moving end can be very easily observed depending upon the patterns or the fringes. You can observe the fringes of different colors. This will indicate very quickly what is the deformation in the members when we are calibrating. So here the major applications is not only restricted for structural problems, even though if it can be applied even for fluid problems, or even it can also be applied on a notched problems. This is one such kind of plate. If the plate is of uniform cross section, then whatever the stress which you are applying, we can directly consider the stress equation sigma is equal to F by A. But whenever there is a stress concentrating problem, such kind of holes or voids which is been in the module or in the structure, so because of this kind of discontinuity, there is a stress levels will be varying. So in this condition, photoelasticity can be applied for such kind of member or a prototype member, and we can analyze the stresses and the deformation in the member. So the variations in the colors is nothing but the fringes you can observe here, the fringes or the patterns. Fringes is nothing but the patterns you can observe in different colors. So this variation in the colors as well as the fringes will indicate what is the stress developed in the member. Similarly, you can observe a C-shaped model, a rectangular body which is having a contour, C contour, and here how the stresses and the deformation is been distributed can be calculated or can be observed very easily by your photoelastic technique. And along with this one, the photoelasticity technique can be can be used to determine the residual stresses developed in the lamp bulbs. Residual stresses which are developed in the lamp bulbs, which are being because why this residual stresses is developed? This is such kind of a manufacturing process. In the manufacturing process, there may be stresses developed in the member. So for all these such kind of problems, we can determine the stresses in the member very easily and quickly by using photoelasticity technique. Now, we need, as a beginning itself, I have indicated the major source for this photoelasticity is nothing but the light source. Only because of the light source I can observe how the pattern or the member is behaving. Suppose if I am observing a light source from one end, if I am passing a light, the light is always tended to scatter or propagate through the space in a periodic manner, which has been in the direction. I can observe the direction here. In Z direction it is propagating. Let y be the magnitude of the disturbance. Then the y is the function of Z in the Z direction. So this amplitude value is regularly repeated in the intervals of Z. Let lambda be the wavelength, and which is nothing but the lowest value of the interval. You can observe here the lambda, which is the lowest value of the interval, and time tau be the time period. And along with that one, we can consider c as the velocity of propagation of the disturbance. Then the propagation of the disturbance lambda can be calculated as lambda is equal to c into t, that is velocity into time period. Then we need to study about to calculate the source from where the what you call as rays are propagating and how they are moving from one point to the other point, and whenever this source or the light rays falling on a member, how the stresses are developed or how the behavior or how the stresses can be observed very easily, we can see through this one. Now let us consider a source of light at one point and which is allowed to pass in the direction either x direction. Then the disturbance will travel outwards in all the direction, and if the medium is isotropic in the sense it is having all the properties throughout the system, having the uniform properties. The speed of propagation of this disturbance will be the same in all the directions. Now we can observe here the disturbance which is traveling from a source to the other end will be formed in the form of diverging. You can observe here in the diverging spherical waves. And this locus, if I draw a locus points which will be having the same magnitude of the disturbance, which is known as wave front. This is known as a wave front. And these wave fronts you can observe many such kind of wave fronts which are a concentric spheres with the sources at the center. Here you can observe the concentric centers. This is center source, and it will be having the concentric spheres at the center. So here the propagation of this source always will be in the direction perpendicular to the plane, and is called as wave normal. This is a normal. Now let us consider a plane wave. Here we can observe here a plane. You can observe here the plane wave where the wave is propagating in the z direction with velocity c. The wave front is parallel to xy direction, as in the previous slide I have indicated. It is in the direction of z. So at a time t is equal to 0, let the disturbance y be given by the equation y is equal to f of z, that is a function in z direction. Then after a certain time t, the disturbance will have traveled a distance c into t, that is the velocity into time. Therefore the disturbance at a point can be calculated as z is equal to z dash plus ct. Hence the disturbance at z at a time t can be written as y is equal to f of z minus t, f of z minus t. Similarly, for a plane wave traveling backward, the fundamental equation can be written as y is equal to f of z plus ct. Now equation 3 and 4 represent the plane waves which can easily be since z is equal to a constant value representing the plane parallel to the xy plane. Therefore, the fundamental equation of plane wave propagating in the direction with the direction cosines can be written as J is equal to f of Lx plus My plus Nz minus Ct, where a function f of z which is periodic in z, the periodic being lambda can be expanded as in the Fourier series as f of z is equal to a naught plus summation of m is equal to 1 to infinity am cos 2 pi m divided by lambda into z plus epsilon m. That is the sixth equation. For a periodic wave traveling forward with a velocity c, the Fourier expansion will be considered as f of z minus ct is equal to a naught plus summation of m is equal to 1 to infinity am cos 2 pi m divided by lambda into z minus ct plus epsilon m. Therefore, the typical fundamental light wave propagating in the z direction can be taken directly as y is equal to a cos 2 pi by lambda into z minus ct plus epsilon. This is the total light wave equation which can be taken in z directions. Because we are taken only in z direction, so the light wave equation propagating in z direction can be taken as y is equal to a cos 2 pi by lambda into z minus ct plus epsilon. Next is the nature of light. See, the light source consists of two vectors, that is, one is the electric vector and the magnetic vector. And here the light waves is again the light source is nothing but the disturbance which can be represented by means of light vector. Light vector which is perpendicular to the direction of propagation. Always the light vector is perpendicular to the direction of propagation. Hence the light wave is known as electromagnetic disturbance, which propagates through space with the electric force vector E. You can observe here electric force vector E and magnetic force vector H. Both are in perpendicular direction to each other. So these vectors, as I told, they are mutually perpendicular to each other. Now we need to determine the fundamental equation for light wave which is traveling in z directions. Let y is equal to a cos 2 pi by lambda z minus ct plus epsilon. That was the previous one from the light source. We have taken the equation. For a given value of z, the above equation can be written as y is equal to a cos 2 pi by lambda ct plus epsilon 1. Then where epsilon 1 is same is some constant, that is a strain constant value of the strain. Therefore, from the above equation we can represent 1 by T is equal to C by lambda, that is equal to frequency of the light which is traveling from one end to the other end, or where the frequency it is stated as a number of wavelengths traveled per second, and 2 pi f is the quantity in terms of radians per second, which is called as circular frequency. Then the above equation can be written as y is equal to a cos omega t plus epsilon 1. Here the function can also be used to represent a plane harmonic wave. It is y is equal to a sin omega t plus epsilon. So this is what the source of light. For this you can represent these equations. Next one is wave theory of light. See, the theory of photoelasticity is based on the wave nature of light. In general, the light wave is regarded as sinusoidal electromagnetic waves, which is having transverse amplitude A and a longitudinal amplitude, that is the wavelength as lambda, propagating in z direction with velocity v. A wave propagating in the positive direction may be represented in trigonometric notation as a cos phi is equal to a cos 2 phi by lambda into z minus vt, which is called as the phase wave of the, where phi is equal to 2 phi by lambda into z minus vt, which is called as the phase of the wave. Therefore, we need to understand certain terms which are related for the wavelength and speed. One is the ordinary frequency, which is given by f is equal to v by lambda, that is a linear velocity by the amplitude. And angular frequency, we can write it as omega is equal to 2 pi by v by lambda. And wave number, we can write the equation as k is equal to 2 pi by lambda. And the above typical expression of light can be written as a is equal to ae to the power of I phi, that is equal to ae to the power of I 2 phi by lambda, 2 pi by lambda into z minus vt, or I can write it as ae to the power of I into kz minus omega t. Now the next is stress optic law. See, by using the light source, I need to determine what is the stress developed in the member. To determine this one, we have a stress optic law. See, the above figure, you can observe two discs. See, the first one is a unstressed material and the other one is the stressed material. This is the unstressed material and this is a stressed material. See, when the thin disc is subjected for load such as the principal stresses, then the principal stresses I can consider it as sigma 1 and sigma 2. So because of the application of these stresses, the refractive index of the material changes, which is changes in the direction as in the normal direction. I can write it as the refractive changes in the refractive as n1 minus n0 is equal to c1 sigma plus c2 sigma 2, and the second one, which are normal to the stresses. Second one, n2 minus n0, I can write it as n2 minus n0 is equal to c1 sigma 2 plus c2 sigma 1, where sigma 1 and sigma 2 are the principal stresses at a point in the material, and n1 and n2 are the refractive indices of the stressed material. Then sigma 1 and sigma 2 are the principal stresses. C1, C2 are the stress optics of the coefficient. Then the basic for a stress measurement technique can be written as, be considered as equation. We will subtract equation 1 from equation 2. Then I can write it as n2 minus n1 is equal to c1 minus c2 into sigma 2 minus sigma 1, where n2 minus I can replace, where c2 minus c1 is nothing but c, that is a constant. When normal stress sigma 1 is greater than sigma 2 and velocity propagation of light wave associated with the principal stress, then such kind of what you call as pattern is called as positive bifringence. Bifringence is nothing but the patterns which is being observed on the member. Then the two components of light vector along the principal's directions I can written as delta is equal to 2 pi hc divided by lambda into sigma 1 minus sigma 2. Here in this equation, where h is the thickness of the module and delta is the magnitude of relative retardation. Therefore, equation 4 shows the relative retardation, that is with respect to the difference in the principal stresses sigma 1 and sigma 2. If photoelastic module material exhibits a perfectly linear elastic behavior, then the difference in the principal stresses is principal strains can be written as epsilon 1 minus epsilon 2, which can also be measured by establishing the value n. Therefore, the relative retardation can be written as epsilon 1 is equal to 1 by E sigma 1 minus mu into sigma 2. And on elaborating, sigma 2 is equal to, similarly for the second strain element, sigma 2 is equal to 1 by E sigma 2 minus mu into sigma 1. Therefore, difference in the strains can be taken as epsilon 1 minus epsilon 1 minus epsilon 2, that is 1 by E 1 plus mu into sigma 1 minus sigma 2. Therefore, epsilon 1 minus epsilon 2 can be written as n into epsilon f by h, or we can replace epsilon 1 minus epsilon 2 by epsilon f, that is the material fringe value in terms of strains, 1 plus mu by E into sigma f, where mu is Poisson's ratio and Young is the material property, that is the Young's modulus. Next topic is polarization. See, from the beginning itself, we are discussing about the light source, which is electromagnetic light source, which are been propagating in the direction of, which will be in the direction perpendicular to the propagation of the directions. See, for an ordinary light, the orientation of the magnitude vector in the plane perpendicular to the propagation direction is totally random. But if the tip of the light vector is forced to follow a definite law or a different direction or path, then the light is said to be polarized. So here there are different types of polarized lights. One is the plane polarized light, where the light rods are restricted to move in only one single direction, then such kind of light is called as plane polarized light. See this one here, the light is only subjected to move in the direction in only one plane. So you can observe the plane of the polarization, and always it is restricted to move only when in the direction there is a single plane. Then such kind of light is called as plane polarized light. And the second one is elliptically polarized light. When two plane polarized lights or plane polarized waves are added together, or neither in the phase nor in the same plane, which are a different plane, are combined, and a special kind of rotating wave can be observed. Such kind of wave is called as elliptically polarized wave. And third one is the circularly polarized light. You can observe clearly here the when two such kind of plane polarized waves are with of equal amplitude are exactly combining, then the exactly of 1/4 of the wavelength can be observed here. It can when these two are combined, such kind of polarized light is called as circularly polarized light. So this is what the how the light can be taken into three categories. One is the plane polarized light, elliptically polarized light, and third one is circularly polarized light. Next one we'll be dealing with the optical elements. There is a for the photoelasticity optical elements. What are the different types of elements? Under that you can observe one is the polarizer. Here a polarizer is an element that converts randomly polarized light into plane polarized light. See, whenever the single light wave with arbitrary oriented wave amplitude approaches the polarizer from the left, the parallel component is passed but the perpendicular one is rejected. Then the light emitting from the polarizer is therefore called as plane polarized light. Okay, we will continue with the next class of what are the other elements of what you call as optical elements of photoelasticity. Thank you.